Hello, everyone. My name is Yipai. I'm a former student of Professor Michael Yu Wang, and right now I'm at Daimon Robotics, and it's a robotics company in China, and we are doing tactile sensing manipulation. So yeah, a little bit about myself. I'm a PhD graduate from Professor Michael Yu Wang from HKUST, and now I'm a co-founder of Daimon Robotics, and I'm leading a tactile sensing team here at Daimon, and we work on tactile sensing, and we use tactile sensing for robotic precise manipulations. I guess that's a quite similar background with every one of you here. Um, and today's outline, I'm going to introduce several research outputs from back in the university when I was a PhD student. And I will also talk a little bit about what our company is doing right now, give you a overview. First, I worked on tactile sensing, and particularly I work on vision-based tactile sensing. The tactile sensing, I hope everyone in this room agrees that tactile sensing is important and indispensable for robotic manipulation. But I'm not sure if everyone is really, because right now there are kind of different approaches. Like a lot of people say, oh, vision models are great, and we just use vision models to do robotic manipulation and can solve everything. And some people don't agree with that. I hope everyone in this room have this have the agreement that tactile sensing is important. Human level of tactile sensing is high frequency, high resolution, and with high accuracy, we can do a lot of tasks without tactile sensing, we cannot, for example, environment exploration, object in-hand manipulation, and also especially tool using in different tasks. And for conventional tactile sensors, majority of them, they are using electric signals, which means the design is complex because basically for every point of measurement, we need to have a whole circuit to support that. And also the fabrication is complicated for those number of different circuits. And the performance, especially in spatial resolution, is quite limited. And also the wiring is a little bit difficult for mass production. And then we have the new trend of vision-based tactile sensing, which in particular, we might be familiar with gel sight and also several other variants of gel sight, for example, gel slim or digit. They are all using vision-based sensing principle, meaning they're using a camera to capture the elastomer deformation, and using image processing and computer vision algorithms, we can reconstruct the surface deformation, and therefore we can interpret it as a tactile signal. What we were doing back in the university is we use a similar kind of approach. We use vision-based principle, but we are not using the photometric stereo for the deformation reconstruction. The motivation is, so first of all, for vision-based sensing, the camera itself is always capturing a 2D image. It's not 3D, unless you are using ToF cameras or stereo cameras, but they are expensive, and they are sometimes they are too bulky to use for tactile sensors. So to utilize the simplest cameras, which is RGB cameras, we only get the 2D images. And extracting 3D deformation from this 2D image is the key in vision-based tactile sensing. Gel sight, for example, it uses the photometric stereo. The change of colors will be interpreted as the surface deformation, which is the red one over here, the gel sight type. And there is also another type, which is, I think, roughly 2004, a group of Japanese researchers, they invented this gel force sensor, which used a lot of sparsely distributed markers. And by tracking the motion of these markers, we can also reconstruct the surface deformation. For gel sight, it's dense in the information, meaning every pixel has its own deformation. For gel force, we don't have all the pixels, we only have the deformation for the markers. So gel force is sparse, gel set is dense, but gel force can reconstruct the 3D deformation. But gel set, because from the colors itself, we can only reconstruct the normal force, but not the shear force. For shear force, gel set still refers to the distribution of the markers. And we used a kind of a third approach, not really the gel force type and not really the gel set type. We call it DM tag, which kind of combines both. We use markers, but we are not using a sparse distributed markers. We use a dense color marker, which by tracking the motion of the markers, we can also reconstruct the dense 3D deformation of the sensing surface. And here is a kind of overview of the structure of the sensor. Here we can see there is a random color pattern, and we use a camera to capture the motion of the markers. And then for here, the optical system, we don't require different colors anymore. So for this optical system, we just use normal LED lights just to provide enough lighting for the camera tracking. To capture the motion of the markers, we use a dense optical flow algorithm. And by tracking the motion of the dense color, we can reconstruct the 3D contact. But there is one potential limitation for traditional kind of optical flow algorithms, meaning if you think of it, optical flow algorithms, they were initially invented to track the motion in 3D world. It's in a rigid world. But however, for tactile sensing, it's kind of different because it's not rigid anymore. It's an elastic surface and it's deforming. So there are a lot of nonlinearities, and basically the pattern you are observing is always changing. It's unlike for optical flow, you are tracking a rigid and not deformed object. For the pattern we are looking at, it's deformed and its deformation is nonlinear. So we used an adaptive strategy, meaning we are not capturing the optical flow between an uncontacted image and the contact image. We are tracking the optical flow between the initial image and also several intermediate images. So basically, it's like we are breaking down the whole optical flow, the whole deformation into different pieces. And by tracking each piece separately, we kind of get a small linearized version of the whole deformation. And therefore, the tracking, we can observe from the results here, the tracking looks more realistic compared to the just using the optical flow from the initial and the current. But however, just tracking every frame to frame optical flow, we might get an accumulated error. So still we need some kind of adaptive strategy to constantly adding intermediate frames and also constantly removing several intermediate frames in order to get a fixed number of frames in the middle.
So Dr. Duke,
yeah,
ask you a question.
Sure.
So this image down here on the bottom right, I think you're saying shows the difference between.
This is a conventional one, and here is after the adaptive. Especially, I think we can see for the which one is more obvious here, but yeah, maybe this one. For the conventional one, you see there are a lot of artifacts here, but for this one, it's actually more realistic, corresponds to the real deformation.
So I'm not used to seeing these kinds of images. How do I know that one is more realistic or more?
Yeah, it's kind of qualitative, not really quantitative, because we can sort of guess what should be the real deformation. At least the edges should be sharp, right? The overall shape should be reflecting the real contact shape. But if we use the conventional ones, we can see often we cannot see the overall shape from the flow itself. But for the adaptive one, the real shape is recovered. That's really a kind of quantitative measure. Yes, and after we get the overall 2D deformation, which is the optical flow, we used a feature called Gaussian density to measure what is the real contact depth. So if we think of it, when we have something that is pressing on the surface, we can observe the overall flow is kind of expanding, right? It's expanding over some contact center of contact. And this Gaussian density is helping us to measure what is this kind of expansion. So if you imagine the pattern when it deforms, basically the distance between each dots will be larger. And Gaussian density is measuring that. It's treating every pixel as a particle and measures the relative density of these particles. And in the end, if we plot the density versus the actual contact depth, you can see a quite linear graph over here. So if we use, so this is just to use this linear relationship. If we use a linear relationship between the Gaussian density and the contact depth, we can see the real contact depth is really covered, is really recovered pretty well. We can see the shapes of these triangles, of these cross, and the dots. And also, actually, from this graph, we cannot see any information about what is the platform that is fixing the indenture. However, we can see several squares here, right? The squares is actually the real the surface that the indenture is mounted on. We can, oh, here it's kind of obvious, right? Here that we can sort of see a square over here, but it's not that obvious. But after using the measure of expansion, the Gaussian density, we can also reconstruct this different multi-level indentation structure. This is a pretty nice feature. So this is how we recover the real contact depth from the optical flow. And but it's that is kind of a heuristic. We measure the expansion, and using that expansion, you fit a linear relationship between the expansion and the contact depth and get some kind of information from it. But it's not really a rigorous calculation. Here we have some rigorous calculation. We use an optimization-based pipeline to reconstruct the real 3D deformation. So the goal is we want to find a smooth 3D deformation on the tactile sensor itself. Smooth is because the surface itself is continuous and should be smooth. And the known parameters we have is first we have the 2D flow, and we also have several camera parameters like K, R, and T, intrinsic and extrinsic parameters. And what we got from the Gaussian density is a rough contact depth. And this is also useful information that we want to utilize. And we formulate all of the information we have as an optimization problem where we want to find a smooth 3D deformation. And the constraints we have is first, the depth should be constrained between 0 and the depth we have from the expansion. And we have the flow constraint, meaning the final 3D deformation we obtained should be the flow that can give me the real 2D optical flow that we measured. And the last constraint is we hope the maximum contact depth is consistent with the maximum with the result that I get from the previous one, from the Gaussian density, the expansion measure. And this formulation itself is a linear program, and after solving it, we can see we can obtain a much better contact reconstruction, especially when we encounter a different amount of shear. So here is the same. They were generated from simulation. All of them, they are the same contact shape, which is the same. This one, the ground truth here. And we are not only making contact in the normal direction, but we are also, after making the normal contact, we are also moving along the surface. So there is also a certain amount of shear force. We can see the Gaussian density gives us a rough measure of the contact, but the after the optimization algorithm, our estimated contact depth is much closer to the ground truth. And also, in the same time, we are measuring the 3D deformation. So the shear force and the contact depth is the normal force. We can reconstruct all of them simultaneously. So this optimization algorithm gives us basically a 3D contact point cloud. And using this point cloud, we can do a lot of things. We can do ICP matching for contact tracking. For example, here we are making contact with a known indenter, and then we can track the contact orientation, contact position on the tactile sensor. And we can also do a more accurate force estimation, because now we have decoupled the 3D deformation. So the 3D force should be only correlated with the corresponding axis, so we can have a more accurate force estimation. And we also put this sensing method into different kind of robot components. For example, not limited to robot grippers, but we also have the robot arm and robot foot. For example, this robot arm is what we built, and it's the same kind of tactile skin on the link surface, but it can be used as one link of the arm. And we did the 2D to 3D, 3D to 2D calibration. So everywhere on the surface you touch, we can localize where the contact is, and therefore can avoid collision or can do human-robot interaction through the contacts. Here is one experiment video. We can detect where the contact is made and then move backwards towards the opposite direction. And we can also do contact following. So we can get the contact location and direction and do the corresponding actions. Yeah, and we also
Can I ask you a question about that?
yeah.
Before we move on?
Yeah.
So much material here. Some I'm trying to save for the end.
Yeah.
Is this a hollow tube? What's the optical?
Yes, it's hollow. So the camera is basically looking inside.
Is the camera top?
Yeah,
and
top.
down?
Yeah.
Are there mirrors? Or anything?
No, it's just I think I
wide
have one.
Angle.
Yes. The camera is here and it's looking upwards, and this is the kind of plot where the camera can see.
So most of its field of view, there's nothing interesting. It's just the other.
Exactly. And here we also quantified this. So here, these dots, they are the dots that we use for calibration.
Okay.
And here, the center, we can see it's nothing there. And we also actually quantified what is the error for the calibration. We can see the error for the centers is actually larger, because here it's
So you have better resolution. Closer
yeah,
to the
here
camera.
better resolution. Yeah. Yeah, we also put this kind of surface underneath a robot foot. And we designed a 2 degree of freedom single-legged robots to do robot balancing. Here we use the same pipeline, but we use instead of using the Gaussian density feature or the extracted 3D deformation, instead we use a convolutional neural network, which can output two angles. Here is a foot surface, and imagine if this foot is stepping on a surface that has some angle which is not aligned with the foot itself. So from the tactile signals we can get, we want to estimate these two angles, basically the angle between the surface, the horizontal line and the foot, and also the angle of the surface that the foot is stepping on. And the result shows a pretty good estimation result. We can control the error in degrees within a half degrees. And once we get these two angles, they are quite useful to us because we can do robot lag balancing. For example, imagine if the surface itself is changing the direction, because we can estimate those two angles, the robot can try to control itself so that the difference of these two angles is minimized, and therefore the foot can be balanced. Another thing is, imagine if we want the leg robots to step onto the stairs. Most of the stairs, they are quite flat, but however, some stairs might have a different kind of a slope on it. And once the moment our foot is stepping onto the surface, we can estimate what is the angle of the surface and adjust itself in order to avoid falling down. However, for example, if we are just using the inertia measurement units, IMU, then we cannot estimate the surface, and therefore the robot will often falling down. For a summary, we proposed a new sensing, tactile sensing principle, which we call it tactile flow-based, and it's using computer vision and random color pattern to get the 3D deformation on the tactile sensor. It requires only a monocular camera and also normal lighting. Therefore, this sensing method can be more easily extended into different applications. And we provided several different signal extraction methods. We have optical flow, we have method to get a contact depth, we have method to get the 3D contact point cloud. And we use this sensing method to robot arm, robot foot, and also initially the robot grippers for tactile manipulation and robotic applications. Here is actually another kind of sensing principle we also developed. It's called visual tactile dual modality sensing. The motivation is, if we think of vision-based tactile sensors, most of the time when there is no contact at all, the camera is looking at a surface where there is no information at all. And it's a huge waste of information bandwidth. And we want to improve that. So our approach is we intentionally make this elastomer transparent. And instead, we are not using visible markers. We use the markers that are fluorescent towards UV lightning. And when the light is on, we can see the markers here showing in the blue colors. And when the light is off, it's totally transparent, and we can use it as a normal camera, like a wrist camera. Therefore, the information bandwidth can be maximized. And we also did some quantitative evaluation on the visual estimation quality, and we can see it's not that bad compared to just the camera itself. Although we are adding several different layers, elastomers, markers, the visual information is not really downgraded, and we can still do feature matching. Although the number of features we found is a little bit less than the ordinary cameras, but still good enough for a lot of applications. And from when the light is on, we can get the markers, and then we track the markers to get the tactile signal to do, for example, force regression. And here is a video to show how it works. When there is no contact, the LED light is constantly switching on and off. So it's switching between visual and tactile mode. When there is a contact detected, then it is fixed into the tactile mode to consistently output the tactile signals. And also when the contact is released, the light is back to switching on and off to use as both tactile and visual sensors. So here is a trick, just a trick to utilize the hardware and increase the information bandwidth for vision-based tactile sensors. And we also evaluated the visual and tactile quality for this sensor. So those are all the research work that we were doing back in the universities. And now we are bringing it to a company called Daimon Robotics. And what we are doing in Daimon Robotics is we hope to utilize what we have done back in the university and put them into the commercial product. The first thing we do is we do the tactile sensors. Because our sensing principle solves several different challenges for vision-based tactile sensors. For example, we know for robotic manipulation, we need a high resolution, and the high resolution is required for a lot of fine manipulation tasks, and vision-based sensors can solve that. And for vision-based sensors, usually there is a complex optical path. The optical design itself is complicated. However, for our sensing principle, the optical itself is quite simpler, and we can use it for different robot actuators, for example, grippers, robot fingers, or others. And we also, using our sensing principle, the integration is simple, and the power consumption and also the thermal part is really much better compared to RGB cameras, because remember we are tracking the deformation. To track the deformation, we don't really require an RGB camera. We can just use a grayscale camera, and grayscale cameras, they are in much lower power consumption, and also it's easier for grayscale cameras to do a high frequency sensing. So here, if we compare our sensor with gel sets, for example, we use pattern tracking, and we have achieved the same sensing resolution, but we can achieve much higher frequency, which is 120 Hertz compared to 25 Hertz for gel set sensors. And for the durability, this is a part that we are quite proud of. Gel set itself is great, but I heard everyone is complaining about gel sets. It's quite it's not really durable after several contact. And on the datasheet itself, it's saying 1,000 coin press for the gel set mini sensor. And here for our sensor, we have done over 3 million contact, and it's still working. So this is one part that we are particularly good at. And to achieve this, actually, we sacrificed something. We sacrificed the ability to capture the fine details of the texture. If you have seen the images produced by GelSec, you can see you can capture really fine details. For example, fingerprints. For example, the coin, the structure of the coin. GelSec can do that. Our sensor cannot. But we sacrificed this microstructure sensitivity, and in return, we get a more robust and endurable surface for the sensing. And yeah, here is also a picture that we have also embedded this kind of sensors into the hand we designed. And in the end, we have some videos to show. Here is the introduction for the gripper-based tactile sensor. And we also have another one which is already made into the fingertip. And this, we built this hand, and as well, we built this, actually we built these humanoid robots. So everything here you can see is from our company. Okay, to summarize, we are a group of people that we do robotic manipulation, and we are from Hong Kong, UST. Our aim is to achieve precise manipulation through a high resolution tactile sensing. And vision-based tactile sensing right now is playing a vital role on this journey. And it's currently, probably later on, there are better sensing technologies that we might want to adopt. But right now, vision-based sensing is what we think is promising in the field. Yeah, that's basically everything. And thank you and welcome to raise any questions.
Hi,
Yeah.
can you hear me?
Yes, I can.
Oh, sure. So I have a question is that I see on your robot finger, right? You
Yeah.
need it's like uh, um, it's like it's still pretty thick comparing to our skin, right? Our skin is like several 2 millimeter thick, but your sensor is somewhat, I estimate around 5 to 10 millimeter thick, right?
Yes, roughly.
Do you think that do you think that will be a problem when we are considering like a more wide coverage of this on like the robot body? For example, if we wanted to be the palm, like do you envision like this kind of optical limitation will be a problem?
Yeah, I think that's a good question. As I said, vision-based sensing is currently what is most promising, but it has limitations. For example, as you said, to put it into a small space and also to put it for a large coverage, it's kind of difficult. But for the fingertips, actually, it's fine because fingertips itself, it has some space. Actually, the video here, you can see in this one, the hand itself is roughly the same size as a human hand. And for this human hand, we have some space in the fingertips to put this optical system, put the CMOS into the fingertip. And to put it in the palm is really difficult as there is no space for that at all. And also we really need a large field of view. However, if you think of it, when humans are doing manipulation, quite often what the real contact happens in the fingertips. And also for humans, we have the most tactile neurons in our fingertips, not the palms. The density of the tactile neurons for humans is much lower in the palm than the fingertip. So that's why we are putting the vision-based sensors only in the fingertip. For the palm, often we might need some pressure sensing, therefore can consider some e-skin-based sensors. But so this is really a kind of different sensors is better for different places. So we think for the fingertips right now, vision-based sensors is really good. And also there is a space as well to put the vision-based sensors in the fingertips. Does this answer your question? Okay. Any others? Yeah.
First of all, really great talk, really enjoyed
Thank
it.
you.
Lots of things to talk about and follow up with, and I'll try not to dominate the questions here. Just curious with your, the optical path. So, one of the concerns I have with vision-based tactile sensors is they need free space for the light to flow through and land on a CMOS element, right? And so in a densely packed finger, we're trying to put lots of things in there. You need to leave open space for the light to get. So two questions. So one, do your optics matter much? Are you doing mirrors or anything, or you don't mind if some things are out of focus and some things are in focus? It just doesn't really matter. That's one question. And a second question is, do you see a path to using optical methods where we could cover the whole hand, or is optical methods, they're always going to be for the fingertip and we have to do something else other places? So two questions. Do optics matter, or not really? Things will be out of focus. It doesn't really matter.
Yeah, I think for our method, same as the previous tactile arm, you can see the different regions. Some regions they are out of focus, some are with more precision. I think for our method, it's kind of we don't really require everything is really in focus, as long as we can get the relative motion of the pattern. And regarding and also our method itself, it doesn't actually really require a special lighting. So for the light, the lighting system is simple. We just need the light to make everything light up. And
Right, so you just have to fill that space.
yeah,
Light, so you can see the markers. You don't
yeah,
have
as long
to-
as we can see
you don't
it,
have to
yes.
light through some waveguide
Yeah.
or something like that.
Yeah, that's one simplification compared with gel side, I would say. And regarding the how to make it even smaller, actually there is another work by Professor Wang's group, not my work, my lab mate's work. It's using so there are different optical or camera technologies. For example, there are compound eye cameras, there are pinhole cameras, there are a variety of different cameras. Basically, they are dealing with different designs, different optical designs of the lens system. So therefore, those lens, they can really reduce the sensing, the amount of range required for the sensing, and we can make it really small. In our paper, not our paper, actually, Professor Wang's paper, it's 5 mm thickness for a fingertip tactile sensor. So, so what I would like to say is by using different advanced optical or camera technologies, we can really reduce the size of it.
So and I think you've already done so impressively just with your fingertip here.
Yeah.
Very small, and you've got a camera.
Yes.
And some kind of lens.
Right now this one is using just normal cameras, but we managed to customize a very small camera, and it's quite a short focus, so we can observe the surface really clean.
Yeah. And so the camera is based here, but you're covering I can't remember, is it a flat patch or is it a rounded patch on the?
I don't know if I can.
On the fingertip one.
Oh,
the other ones were flat.
Oh, I think I have yeah, here. So the camera is basically here. It's this is the hole for the camera. It's looking
out that way.
Yeah.
And the finger itself is rounded.
Yes.
And so it's very close to some dots and very far away from some dots, but it sees them all well enough to still.
Yes. Okay. Yeah. It's still like, I would say the resolution itself is still higher than some of other sensing methods.
Is there anything else in there besides a camera? Anything that's sort of important to the way the optical sensor works besides a camera, a light source?
Light source is okay.
And then the rounded surface with markers on it.
Yeah.
And you have an outer surface that's the black, I don't know, rubbery kind of material, I guess.
Yeah.
But there's no other optics or anything else?
No, nothing else. Yeah.
Just have a really small camera.
Yeah.
Thank you.
Yeah.
What kind of calibration do you do for each like sensor you make?
Yeah, the calibration is, as Kevin have just pointed out, there is a round surface. So to put this round surface onto a flat region that our camera would like to observe, it requires some extrinsic camera calibration. This is one thing. And another thing is quite often when we are doing the real manufacturing, the pattern itself might be kind of in different places. Although we want it to be always the same, but it's manually stick onto the surface. So there are some slight changes, and we need to we are now doing an automated calibration process, meaning we try to find out where the boundary of the pattern is and to localize it and put it just warp it into a square image. These kind of calibrations. And another thing is in terms of the material calibration. So right now we are not really doing the actual material calibration, but to do a mass production of these tactile sensors, material calibration is really important, especially if we want a consistent force outputs. So that part is what we are doing, but it's not onto the product itself.
Different layers for each finger.
Yeah.
I saw that the colorless layer is like hydrogel, yes?
You mean
Could you
this
please
one?
Yeah.
Yeah.
Could you please tell me why you have like 3 layers and
This is for protection.
okay.
Yeah, and this is accurate for supporting the structure.
But the gray one?
The gray one? This one?
No.
Uh,
Second, yeah.
This is the pattern, the color.
pattern.
Yeah, it's a color pattern. Yeah, there's a question. Yeah.
The method to estimate some contact forces specifically?
Yeah, so we are planning to. Actually, a lot of people who are using these sensors, they are asking what is the precision for your sensor, like in terms of force. But everyone who is working with vision-based tactile sensors, no, we don't really have this force. We just have deformation, but we can calibrate the deformation into force. But if we just do the calibration from the deformation to a single force output, it's kind of the dimensionality is reduced because we can only output total force. There is no such device that can help us to measure the actual distributed force on the surface. So the only thing we can do is we can calibrate it and output the total force to the customers. But I always recommend not to use them because it's a reduced information. So I don't really recommend to use the force output. But we are adding it to the products. Yes.
Yeah, so just to follow up on that, I see we have a question online here. So we spend some time thinking about how do you actually get force from sensors like this, and we get frustrated by the hydrogels and the elastomers and all their terrible mechanical properties, their hysteresis and creep and other things. I suspect a lot of people think, well, we don't need force, we'll get something and we can use that something directly, and maybe never translate it directly to a force and a torque, because we know that the properties of this material are not ideal, especially their time response. So do you agree with that sort of?
Yeah. Yes.
We do have a question online. How accurate is the force torque sensing of the sensor? And would the non-linearities of the silicone influence the accuracy of the measurements?
Yeah, it will. So that's why I say we are adding a extra calibration for the materials itself, and also in terms of the force accuracy. Right now, we are having in our labs so the sensitivity is roughly 0.2 Newton, and that is given ideally I should say pressure, but we are talking about force, so this force is generated by a indenter that is 1 centimeter squared contact area. So in this area, the sensitivity is 0.2 Newton, and the precision for the force is roughly 0.1 Newton. but this is just a total force, not really in terms of a distributed force. Yeah.
You briefly mentioned the dual modality.
Yes.
Tactile dual modality. What do you think these other modalities are important to your sensing?
Yeah. A lot of people are asking whether we have temperature for vision-based sensors. I think right now we don't have, but we can add it. We can add some other kind of sensors to capture the temperature, not just for, I think it's not just for the output, for the sensing output, but it also helps us to figure out what is the temperature drift on the surface, because we observed, although vision-based sensors is great, in different scenarios, for example, when we have extremely low temperature or we have extremely high temperature, not really extremely high, but like 50 or 60 degrees Celsius, then for other sensors, the signals might be changing a lot. But for vision-based sensors, it's better, but still there are variations in the signals itself. So knowing the temperature can also help us to calibrate the material property in order to produce a more consistent tactile information in different scenarios. So I think adding temperature is helpful, and it's not only helpful for customers, but also helpful for our calibration. So adding temperature might be useful. And I saw there are some works that are adding microphones. I'm not sure. I think microphones might be too noisy if the environment is not really a controlled environment. So yeah, these are two mostly asked modalities we have.
Speaking of noise, if your environment has fluorescent lights, does that light up your markers too, or it really needs to be the ones that you're controlling?
Yes, because UV light. So there are not this kind of light that can light up the markers. Yeah.
Does this still work outside with the UV light from the sun comes in?
Yes, from the UV light from the sun, it is not light up. So it really requires some power for it to be visible. Yeah. Yeah.
Was there what engineering considerations were there when you were choosing your elastomer for your finger, and like what kind of stiffnesses were good for?
Yeah, right now we are just using our heuristic based on our experience, because right now the products you see, it's our first generation of products. We are planning to make this available to all the customers, and then they will have feedbacks. For example, some of them may say, oh, we want more sensitivity, then we can make it softer. Or some of them may say, oh, we really want to lift heavy stuffs, and we want it to be in a larger force measurement range, then we can make it stiffer. So it's based on the feedback from the market.
So you say your sensor, if you go back to that slide where you give us the specs, you say 120
Oh, yeah.
hertz pattern.
This one?
Are you sending back, what are you sending back at 120 hertz?
We are sending back the raw images in 120 hertz, and our processing algorithm can also run in real time to output all the 3D deformation that I mentioned.
Okay, so at 120 times a second, you're sending back a 320 by 240 image from the finger.
Yeah.
And then the processing of that to turn it into forces or indentation or whatever.
Yes.
Happens somewhere else.
Yes. Right now we are using GPUs, and we are planning in our next generation. We are having a chip that we customized, and we run all of the algorithms on that single chip, and it can stream all the data back to the laptop or workstation. It doesn't require the.
So for this robot hand now, if there's one of these in each finger, maybe
Yeah, most of the time we use three.
three. Okay,
Yeah.
so three.
And then we
there's
have
3 cables or
yeah. Right now we have one single board, not for computing, but for combining all the 3 and then just
in the
be
hand
back
or
in
at
one.
the hand, and then that comes back as a
Yeah.
cable that goes to the user's
Yeah,
GPU
yeah,
or
yeah.
something like that.
Yeah, that's it. Yeah.
Oh, also. Sorry. You mentioned you're proud of the durability of the sensor.
Yeah.
And last to much more cycles other products. But you sacrificing the industry.
Yes.
You cannot detect the textures or stuff like that.
No, not that fine textures, but we tried Mahjong, it's working fine. So yeah, not that microstructure, but larger structures.
The resistance to the sharp edges and corners. I found those sharp edges and corners for the objects will destroy the.
Yeah.
Make fast.
Yeah, that will be a question. So I think a more so that also is a question about the specification. So in the specification, what we are really talking about should be all in pressure, not really in terms of force or it's not really good. We should be talking about pressure, but right now we are not doing it. I hope we can do it sometime in the future. We can quantify the maximum pressure we can have, the pressure range we can have, the sensitivity also in terms of pressure. I think that will be better. Then everything will be quite manageable.
Show us the
Oh.
sensor and the hand sensor first.
Since this one. Okay, but I need to use another computer.
No, just call it hardware, don't.
Oh, okay.
That's what the
So,
cable. It was
yeah.
circular, the-
So right now it's in the shape of this. We have different form factors. This is the middle one, and we also have a smaller one. We also have a larger one, a bit larger. This is usually used for grippers.
So there's a similar cable to that coming from each of these fingertips?
Yes, right now, yes.
What is, okay, so what is that? B or what's the?
Here we are sending the signals in MIPI,
Yeah.
and we have several camera drivers inside of the palm, and we are having USB output, and then there is another board that I talked about to combine all the signals and output to the users.
In your review of technologies for tactile sensing, you left out probably several things, but one that's jumped out to me was magnetic approaches.
Yeah.
And I bring this up in part because at the conference we were just at.
Yes.
Xhand is talking a lot about their magnetic tactile sensors, and there are other companies there like eኢና Robotics that do magnetic.
And also Meta is
And
doing
Meta,
yeah.
yeah, there are others. So is there a reason you didn't mention them, or just you were giving them examples? And what do you think about?
Yeah, here in the examples, I mainly talked about the electric ones, not the magnetic ones. But for the magnetic, I think they are quite good right now. But in terms of because I think still the sensing resolution is really important in a lot of really fine-grained manipulations. And for these tasks, magnetic will be a bottleneck for the sensing capacity. And also, I think for the signal itself, optical signals is better to be used for especially industrial applications. The magnetic, industrial environments, it's not that robust to all these kind of magnetic or electric shock or the tool usage, because all the tools basically used in industry, they are in metals, or they will create the interference on the signals. So yeah,
I was actually curious about that because I went to one of the booths.
Yeah.
Asked them to hold some ferrous material or
Yeah.
magnets close to their sensors. This is eኢና.
Yeah. I
Looked
see
like
that
they're
as
able to
well.
compensate for it somehow.
Yeah.
I don't know how.
Yeah, we can compensate, but in my mind, it's not always really possible. But yeah, different approaches. But I think magnetics right now is really doing a great job. But I would say we bet on the optical ones that will be leading the next generation of tactile
Do you think
sensors.
if I take your robot hand and grab a hammer and pound on something hard,
As long as the structure doesn't fail, then
I'm not
should
gonna
be
break
fine.
your
yeah,
camera somehow.
yeah, because the structure is really, yeah, it only depends on the structure. Okay.
If I may add just a bit, the bit of information just for the sake of discussion. This is the research that we have done and commercialized. I'm still a researcher, so I will look at these and I'm thinking about, and we have been talking about that there are issues with the fingertip sensors. And that we want to measure the distributed forces, and we got to measure the deformation. And there are absolutely nonlinear, there are hysteresis, there are viscoelastic, but just like our fingertips. And we deal with similar problems. So our calibrated, most we may calibrate 1 or 2 points. We never calibrate everywhere on your fingertip surface. But now I'm looking to a bit more deeper on human finger sensation measurement and also the feedback of controlled from the central nervous system to do the grasping manipulation. It turned out in our fingertips, very similar issues, nonlinear, hysteristic, viscoelastic. However, our fingertips, we measures far more set of information that we possibly know. We have memories of the deformation of our muscle and finger skin over a period of 0.5 seconds. We remember all the deformation we have done. And we also use the history of historic deformation to feed back to current state of control. And we do computing within our muscles and up to our arms. Most of the things never come to our head. All of these are tremendously remarkable. But from hardware point of view, we seem to have mimicked our fingertips hand in terms of the signal process, information processing, and come back to do the control. It absolutely in the dark. No idea. And whole humans are so good at control our fingertips to do control. So that's a very long range, deep set of issues and questions. I'm hoping that there will be more interest from academia in collaboration with neuroscientists and physiology to look deeper into this, because they really have almost complete understandings. And they're not training anymore for them to do this sort of research anymore, because they think they really have everything studied well enough. And it takes the time for our engineers to pick up from there. Now we have all this deep neural network that might help us to do some decision-making. Use of this all this nonlinear information to do controls. And they're not aware of, so I hardly ever talk to them about all of this stuff. I have not found the right students who are interested in diving into.
All right, I think we're at time, and I know we have a discussion coming up that lots to talk about. So let's thank our speaker one more time.